should end the semester in the same way that we started it, with egregious waste of valuable class time because of my ineptitude with technology. All right, well, we spoke last time. We were ending talking about elimination reactions, and that's where we're going to finish up today. We introduced the idea of the E1cb reaction, in which you have fast deprotonation of the beta proton, the one that's beta to your leaving group. You have an intermediate that's negatively charged, and then you do the elimination of that intermediate. The lone pair electrons that were on the alpha carbon and or on the oxygen can kick down and do the beta elimination to have the leaving group leave. This is called an E1 type reaction because it's unimolecular under certain conditions, and we can explore when that's the case. As it is now, if you're told that the second step there we are. Everybody still see my screen? Sorry, it's doing funny things. Okay, I think we should be back. Is everybody? Can you give me some kind of sign if you can see my screen? Yes, good. Yes, good, bad, no, yeah. Thank you. How do I unmute myself? I don't know what's going on with Zoom. I am sorry. Thank you. You see me sitting here talking and no voice, and that's embarrassing. All right. Where were we? So if you want to derive kinetics for this E1cb reaction, you can use the steady state approximation for this enolate intermediate, and if you do the math, you come up with this expression there, which is sort of where we ended it. Let's talk about under what conditions you might observe different things. So as an example, if under these conditions k minus 1 is much greater than k2, then you can simplify our expression, getting rid of the k2 term in the denominator. And then having just k minus 1 and BH in the denominator. But your text points out that if you control pH in this reaction, based on the relationship that Ka is going to be equal to H3O plus divided times B minus divided by BH, then we can swap out this ratio of B over BH for Ka over hydronium concentration. Sorry, should slide this over because we're going to put Ka here, conjugate of the conjugate acid of your base, and then K minus 1 and hydronium concentration. And if you keep pH constant, then all of this is constant, and you end up with a rate expression that looks like it's unimolecular. and only depends on the leaving group and not on the base. Okay, questions so far? So this would be an example if we set up, yeah, you bet. That's right. That's right. That's why we call it E1 conjugate base. Your text talks about subcategories of E1cb reactions, which got too confusing for me, so I won't attempt to do that. But under different sets of assumptions, then we can simplify our rate law and expect to see different things. In this situation, as we've talked about it, because K2 is the slow step, right? The base is not involved in the rate determining step, and therefore we would call this specific base catalysis, because the base is involved previous to the rate determining step. Other questions? All right. And there are some other subtleties that your text goes into, but I don't want to spend any time on that. I want to talk about the continuum between E1, E2, and E1cb in the same way that we've done it previously with one of these Moore, O'Farrell, Jenks diagrams. In the upper left-hand corner, we're going to have our starting material with our beta proton and our leaving group attached to the alpha carbon. And then you've got a base. And on the x-axis, we're going to have extent of deprotonation. Ah, that was fun. I hold it down and it makes a lovely square for us. So on the x-axis we have extent of deprotonation. This has been called alpha before at various times. And then on the y-axis we have extent of leaving group departure. Sort of 0 to 1 on the y-axis in this direction, and sort of 0 to 1 for the x-axis in this direction. So if we had a situation where the leaving group departed first, you would have a positively charged alpha carbon and a negatively charged leaving group. And that is the sort of E1 pathway. Alternatively, if you have complete deprotonation first on the beta carbon, but the leaving group is still there on the alpha carbon, then this is the E1cb pathway. And then, of course, if you went from the top left diagonal to the bottom right diagonal, leaving group is departed, deprotonation is 100%, and you have your alkene. So there are multiple ways we could get from the starting materials to the products. If we go sort of straight on this line in between the upper right left-hand corner and the lower right-hand corner, this would be the E2 pathway. Okay? Questions about how we've set things up? That's right. Yeah, E2 is an intermediate case between E1 and E1cb. And now we can, with this, other questions. All right, so let's try to think about how various changes might influence the transition state of this reaction. And let's suppose for the E2 pathway, our transition state originally is right about here, okay? So that would be sort of roughly 50% deprotonated and something like 50% leaving group departure in the transition state, which seems decently reasonable for an E2 reaction. Let's talk about changes we might make to the structure of our molecule. So let's first, and I'm not sure how this is going to go. We'll try to use different colors. Let's talk about changing substitution on the alpha carbon. That means going from like primary to secondary to tertiary. Looking at this diagram, what would changing substitution do for the stability of the various corners? Should it do anything to starting material? Yeah, Kim, I see you nodding your head. It's sort of like probably, well, certainly there'd be some change, but it's probably minor. Okay. How about for the carbocation? What should changing substitution do there? Should stabilize it because more substituted carbocations are more stable. So let's just put a blue circle here. And to indicate that by changing the substitution of the alpha carbon, we're taking this corner of our plot and lowering it in energy. What would increasing substitution do to the products? Any ideas? Product is an alkene, so yep, more substituted alkenes are more stable. It's difficult to know, how much we could expect the products to be stabilized versus the intermediate carbocation. Nevertheless, let's just sort of think about the impact of this change. We're taking the bottom edge of this sheet and lowering it in energy. Remember that along the diagonal, lowering energy at one corner pushes the transition state towards the other corner. Right? This is the Hammond effect. If now the transition state is farther away in energy from the products, it has to resemble starting materials that much more. How about what should the extent of deprotonation? I'm sorry. What should happen? I'm sorry, with this lower left-hand corner. What should be the response of the transition state to that part going down? Okay. All right, cool. And again, the relative amounts of this would depend on like how much the lower right-hand corner is being stabilized relative to the lower left-hand corner. Let's say for the moment that, because carbocations should be a little bit more sensitive to substitution than products, alkenes should be, simply because carbocations are less stable. So let's imagine this kind of change. Now we get to do some fun vector math. So what does this do to our new transition state? Can you describe how that transition state might have changed in terms of extent of deprotonation and extent of leaving group departure? Okay, so less deprotonation. What else? Okay, good. More leaving group departure. Thank you, Kim, for being willing to speak up. The rest of you may speak up as well, as desired, no pressure. And, you know, the more we get along this extent of leaving group departure, the more we're actually going to get carbenium character, carbocation character at at the alpha carbon. Okay, so that's cool. Let's think of a few other changes. I'm going to, if it's all right, erase sort of, maybe we won't erase because I want to have all of this in the notes at the end. Let's just copy and paste, and let's now have a different change. What if we, instead of messing with the alkene, or rather the substitution of the alpha carbon, let's now mess with let's try stronger base. Okay, so what if we use a stronger base? Now your instinct tells you what should a stronger base do for an E on this continuum? Just based on your knowledge from undergrad 351. Okay, right, which makes sense. We would have described it in anthropomorphic terms in 351. A stronger base isn't going to want to sit around and wait for the leaving group to leave. It will start deprotonating first. But of course, molecules don't want anything because they are not people, though it's sometimes useful to think they are. So let's just examine, using this diagram, what increasing the strength of the base should do. So who can tell me, how should base strength, let's suppose we make the base stronger, what should that do to my potential energy landscape? Okay, lower, or so if the base gets stronger, is the base more or less stable? There you go. Yeah. So that would be raising the bottom left corner and the top left corner, because the base is there in both cases, right? And let's just say, because the base is the same in both cases, let's say that we're raising both of them by similar amounts. So raising the energy of the starting material should result in a Hammond effect that pulls the transition state to be more starting material-like, whereas increasing the energy of the lower left-hand corner should have the sort of marble on a sheet effect where the transition state rolls away from the change. do the vector addition, and what we find is, fascinatingly, when you increase the strength of the base, the extent of deprotonation doesn't change. Isn't that wild? Extent of deprotonation stays the same, but there's way less leaving group departure in the transition state. Okay, and so that's why this diagram is useful, because you might have been tempted to say, well, if you make the base stronger, there should be more deprotonation in the transition state. And that sounds intuitive, but it's actually not what happens. You increase the strength of the base, extent of deprotonation in the transition state remains the same. It's just less leaving group departure. So let's go ahead. Why does the base do anything to the leaving group? I guess, and you understand how we get it on the plot, so now we're just thinking intuitively. Maybe think of it this way. If the base is weak, the leaving group has to depart in order for the proton to be, has to start to depart in order for the proton to be acidic enough to remove. Right? Protons that are alpha to or beta to leaving groups are more acidic than regular sp3 hybridized carbon-hydrogen bonds because of the sigma to sigma star hyperconjugation with the leaving group. That hyperconjugation should be more important the more the leaving group leaves, and that should therefore make the proton more acidic. So I would say the fact that if a base is stronger, the leaving group doesn't have to depart as much to make the proton acidic. Good. Now there's some sorry, hold on. processing. You can do the same sorts of analyses. Maybe we don't need to draw the diagram because you're used to dealing with this, but let's imagine what would happen if we used a better leaving group. Better leaving group would stabilize which corners of our diagram? Okay, so that would pull down this side and this corner by similar amounts because the leaving group's the same in both cases. Again, we can expect an anti-Hammond effect along the diagonal, but then or rather a Hammond effect along the diagonal and then a marble on a sheet effect for the lower left-hand corner, and we do the vector addition, and we see that the better leaving group has the, and this is again ironic, has the same extent of leaving group departure, but less deprotonation. And I guess I would rationalize it this way. What makes the leaving group depart is the sigma to sigma star hyperconjugation with the adjacent beta proton or proton that's bonded to the beta carbon. So if the leaving group is better, we shouldn't need to deprotonate as much to make it leave. I realize in saying this that it probably sounds like I'm talking in circles, and I may be. So I'm sorry. But I hope what you're learning is that if we think about this systematically with one of these diagrams, we can come up with sensible predictions that you may not intuitively have been able to come up with on your own. The last thing that your text mentions as a possibility, I'm trying not to use red, green, colorblind stuff, is adding an electron withdrawing group to the alpha carbon. And, oh, sorry, no, I was wrong. Adding an electron withdrawing group to the beta carbon. So this would be like if I had an electron withdrawing group here, and that would tend to stabilize the anion while really not doing much of anything else. So in that case, we would expect the transition state to move to more deprotonation and less leaving group departure. And therefore more carbanion character on the alpha carbon. So unsurprisingly, when you just move one corner, you push that's off the diagonal, you push the transition state in that direction where the corner is stabilized. And yes, there we're getting way more deprotonation and way less extent of leaving group departure, meaning we're becoming more E1cb like. Okay. Any questions you want to ask? All right. Well, it might be fun to, I'm going to mark in purple where we said, I'm going to mark in the appropriate color where we said the new transition states were going to be. And I suppose we had the blue transition state right about there. I'm just having to compare with the diagram. So let's now talk about selectivity, because you have learned that elimination reactions are selective for the more substituted alkene because the more substituted alkene is more stable. So let's imagine which of these four situations, situation 1 in blue, where we change the substitution on the alpha carbon, situation 2 in purple, where we use a stronger base, situation 3 in orange, where we use a better leaving group, and situation 4 in pink, where we put an electron withdrawing group on the beta carbon. Let's think which of these transition states has the most alkene-like character. Yeah, the original one. So if you made any of these changes, what would you expect the selectivity for more stable alkene versus less stable alkene to be? I think so. I think that's the way I would interpret it, because all of these are further back along the reaction coordinate than just our original reaction. So I don't know that that's a universal observation. Just be ready to think of the idea that some situations might be less selective than others. For example, in purple, where we changed the base and we made it stronger, it looks like you can imagine sort of some intermediate values of weaker and weaker bases. The principle would seem to emerge that the strongest base would be less selective than the weaker base for the more substituted alkene. Sort of a relative kind of consideration. Okay? All right, so I found that a really useful way to think of these reactions. It's a lot more nuanced than the little table of E1, E2, SN1, SN2, and good nucleophile, strong base, whatever, that we generated in 351. But ultimately, it's more realistic. Okay, questions? All right. Go ahead. Yeah. Okay, so if we put an electron withdrawing group here, and I guess we could label it all over. The question is, how does that electron withdrawing group affect this potential energy landscape? And over here for starting materials, it looks like not much. Over here for the E1 pathway, that would probably be destabilizing. But fortunately, destabilizing this corner is the same as stabilizing this corner. It causes the marble to roll in this direction. Putting the electron withdrawing group here shouldn't do too much to the alkene stability. So the major change is just in this direction. Now recall that the off-diagonal upper right-hand and lower left-hand corner changes to stability here do exactly what you'd expect a marble to do on a sheet. It's changes of starting materials and products that have the Hammond effect, which is you go towards the direction where stability, where energy increased or stability decreased. Yeah, you bet. What else? Right. Well, I suppose all of these are relative things. Like we started with a transition state that was right in the middle. We didn't necessarily have to. So suppose we started with a transition state that was here, fairly E1-like. Now let's talk about what, say, using a stronger base would do, right? If we apply the same sorts of reasoning here, the transition state does get more E2-like because the extent of leaving group departure decreases. So what we said was, so what I told you was true from a certain point of view. No, these changes describe changes relative to a starting point, wherever that was. All right, what else? So you should be aware of the general requirement, stereoelectronic requirement, that for E2 reactions, the beta proton needs to be able to be anti-periplanar to the leaving group. Okay, I assume you know that. If you don't, you need to go look at that in the text and it'll explain it a little bit more. However, there are situations there are examples of syn periplanar elimination. It's the exception rather than the rule, but there are a couple of situations when this can occur. Syn elimination tends to occur when anti-periplanar geometry is not possible, but syn geometry is. They can also occur when the base and its counter ion are highly paired. That is, they exist as a contact ion pair rather than just the base on its own and the ion on its own. And then finally, sterics can bias the situation towards syn periplanar syn periplanar elimination. So let me give you an example. One of these horrendous bicyclic systems. We've got a leaving group in a pseudo-equatorial position. Highly paired. So that would be like you've got potassium T-butoxide and the counter ion. Very close together, not separated in solution. Right, good. Less polar solvents. Yep. Good prediction. All right, so this is an example of situation number one. The geometry of this ring makes it so that the proton here, oops, gosh, this makes it so this down proton on the beta carbon is trans to the leaving group, but it can never get anti to the leaving group just because of the ring constraints. In contrast, the proton that's cis to the leaving group lines up with it directly, okay? And so even though the orbital interaction isn't quite as good, you can imagine that if a base removed this proton, electrons in this sigma bond could donate into the sigma star. The overlap wouldn't be great, but it would eventually work. Okay, especially if the leaving group starts to depart, then what you have here is more and more like a p orbital and less like a sigma star. So in this case, yeah, if you do the reaction, what you observe in the product is exclusively the protonated species where deuterium has been removed by the base, and then you have the counter ion. Okay, I'm not going to draw, I don't know why that proton is there. We should have drawn it nicer. I'm not going to draw the particular orbital interactions. I think there's a figure in your book to describe that if that's giving you a little bit of heartburn. Second ion pairing case, an example of that would be the following situation. This is just an example from your text. I don't know why there are two chlorides here. Oh well. But if you can have, if the base is highly ion paired with its counter ion, then if you remove the proton here, the counter ion can help the leaving group leave. And so syn elimination becomes more favorable in that case. Again, not the natural order of things, but you can promote it with in less polar solvents with an ion pair. And the last example is just maybe a fairly esoteric example. There's not a lot of cases where you might observe this was the way things would be. Let's imagine a Newman projection where your beta carbon looks like this, and then in the back is your alpha carbon with the leaving group. And let's just suppose, for steric reasons, that your leaving group is ginormous. It's a tetraalkyl ammonium. And let's just suppose that you have deuterium here and proton there. The conformation that keeps the beta proton anti to the leaving group has some significant steric problems by keeping the leaving group gauche to large things. Whereas if we were to draw the syn arrangement, that would be less of a problem. Okay, so I don't see myself ever asking you to predict when syn elimination would occur, but I could see myself to ask you to I could see myself asking you to rationalize it after the fact. Why might it have occurred here instead of other situations? Okay, so there's more to say, but I think that sort of has to be it. I'm going to pause for any questions you want to ask on this stuff or anything else. Because it would have been impossible to distinguish the syn and anti products otherwise. So if we draw the elimination product from anti-elimination, you've got proton on the same side as phenyl group and deuterium on the same side as the R group. If it was syn elimination, which is favored, the alkene that you would get would be the other stereoisomer. So you just need the deuterium in order to be able to discern between those two stereoisomers. All right. So we've run out of time. Keep going. Any other questions? Okay. So, we can now take a step back and sort of ask, so what? We've run out of time talking about the what. There's plenty of new reactions to learn, and you'll have experience doing that. But I think we've had enough time to talk about the why reactions happen, and the how. You now have mechanistic tools to understand reaction kinetics. You have experiments that you know of that can help provide mechanistic insight. From the beginning of the course, you have some good quantum mechanical intuition to help you understand bonding in a way that combines all the good things about valence bond theory with all the good things about molecular orbital theory. And hopefully you're fluent in both of those worlds and can easily step into one or the other as needed to think about organic molecules. We spent a lot of time talking about non-covalent interactions, which are key and important in understanding molecular recognition and protein folding. With all of that, you should now have the tools needed to understand your own research from a very sort of fundamental physical principles point of view. In the future, you'll take classes on maybe on synthesis, on organometallic chemistry, perhaps on natural product chemistry. You may take Dr. Savage's bioorganic class, but you're going to see these physical organic principles come up again and again and again. This kind of approach to chemistry is really what made me want to be a chemist in the first place. The idea that you could bring some order to the world around you by just understanding the math and the principles that underlie it all. So, yeah, what else can I say? Go forth and do good. Your final I will write and I will give it to you. It won't be due any sooner than the actual day that the exam is scheduled, but I'll have it to you sooner than that. It'll be a take-home exam. You'll take it under the same circumstances that you took the last take-home exam. Anything throughout the semester is fair game, though the course is cumulative, so questions I can ask you about stuff toward the end tends to talk about all of the principles we talked about all the way through. Your final will be worth just a little bit more than a midterm, 250 points. Not significantly more. I will grade it in the same way as I graded your oral presentations and this most recent exam. Rather than taking off -1s here or there, I will look at your answer to each question. I will make comments, and then I will evaluate each question, giving you a score between 1 and 4 that sort of describes the understanding that I believe you have shown. Any other questions? I don't know. That's not a good answer. Let me see if I have it in the syllabus. Okay. Yeah, we are definitely not going to have it exclusively at that time. I will write your exam so that it could have been taken in about that amount of time, but it will be a take-home exam. You can do it whenever you want, as soon after I send it to you, which will be in the next couple of days, and it'll be due then. But you can turn it in whenever you want. Okay. Well, have a... I don't have a very good sign-off. Let's see, back when I was doing 352 in the winter semester, I would always sign off with stay safe, stay healthy, and stay organic. I could sign off with may the force be with you, which sounds like a good sign-off, or I could go the politician route and say, God bless you, and may God bless America. But I'm not running for public office. So I hope you have a very Merry Christmas. I hope you're successful. Please stay in touch, and we'll see you around the 4th floor.